So one thing that we want to do is we want to prove the infinite uncountability of the Cantor set. But in order to do that, we need to build up a certain, a few definitions, some of which have already been covered by the previous. For instance, cardinality. Cardinality of a set is the measure of the number of elements in that set. And we know two sets have the same cardinality if there exists a bijection from set A to set B. Another definition, a set S is countable if it has the same cardinality as some subset of the naturals. Another definition, set S is countable if there exists an injective function from S to the naturals. A set is countably infinite if there exists a bijective function from S to the naturals. But not all infinite sets are countably infinite. And we know this, we've seen an example in the previous group. They proved that the reals are not countable by showing that there does not exist a bijection from the naturals to the reals. And it's a very similar proof to what we'll do to show that the Cantor set is not countable. So, like I said, many sets are uncountable, including the Cantor set on the closed interval 0, 1. We will eventually show this. Keep in mind that in order to do this, we'll need to show there does not exist a bijection from the naturals to the Cantor set. So, all right, we will denote each level of the Cantor set as 0, 1, or C sub 0, C sub 1, C sub 2, and so on to C sub n. So this is C sub 0, C sub 1, C sub 2, and it would continue on. Next slide. Now we want to be able to refer to a specific interval in the Cantor set. So we let I sub nj do that, where n and j are in the naturals or equal to 0. They represent the specific interval in the Cantor set such that n refers to the level that we're speaking of, level 0, 1, 2, and j refers to the specific interval on that level. So for instance, if z is in I sub 2, 3, we know that it's in level 0, 1, 2, and interval 1, 2, 3. Okay. So we want to show that an element of the Cantor set is analogous to a path on a tree diagram, as we've seen. And we'll do this by considering the closed interval 0, 1, continue with the deleted middle third strategy that we've been using, and we will denote a movement to the left on the tree diagram as the left interval to the deleted middle third. So the interval to the left of the deleted third is a movement to the left on the tree diagram, and the interval to the right of the deleted third is movement to the right on the tree diagram. So for all x in C, and for all n, x is in C sub n. So basically we've shown that its location in each piece is described by a path in the tree. So in other words, if you gave me an element of the Cantor set, I could show you a path on the tree diagram that can be represented by that element in the Cantor set. But in order to show that this analogy is completely sound, we need to show three things. One, that a given element in the Cantor set has only one path. Two, if x and y are not equal, then x and y have different paths. And three, for every p in the set of paths, there exists a c in the Cantor set such that f of c equals p. This is the same as saying well-definedness, one-to-one, and onto. And I'm going to show prove well-definedness. So there exists a function f from the Cantor set to the set of all paths in a tree. We want to show that for all x in C, f of x is well-defined. So let x be in C. Suppose P1 and P2 are both paths describing x's location. Suppose by way of contradiction that P1 does not equal P2. then there exists some n and n such that the first time on level n, p1 does not equal p2. This implies that x exists in two segments of the path. Now I'll explain. So basically what we've said is that if two paths represent the same location, we're moving along the tree diagram, but at some point they must be different. And we're saying that x lives in both of those line segments. But that can't be true, that's a contradiction, because we know that these intervals and paths that we're talking about, which are now sort of interchangeable, are disjoint. And therefore, for all x in the Cantor set, f of x is well defined, and we've shown that a given x in the Cantor set has only